parts out too, okay.
Yeah, okay, so here we are, this is week 4, this is lecture 7, and I'm just gonna go through the syllabus. I think we're at the point now, add drop date has come and gone. I think I had one student that may be dropping. We'll see if we can get him back in here. But I think we're moving along pretty well. We've covered a lot of ground so far, and it's time to move on to the next section. So what I'm going to do today, I will get to methanol if I can. If not, all the material's there. But what I do want to do for sure is just go and review the first 2 assignments, show the solutions, go through it so we all know we're on the same page. So that's where we are now. It's week 4. We're starting methanol, but what I've decided to do, at least today, is catch up to where we are, and then on Thursday, we can get into methanol for sure. Coffee man is here. Awesome, thank you. Straight A's, instant A.
I am straight A's, I am the terrible on test. Questions loaded.
Oh, they're all loaded questions. What do you mean?
It's
Okay.
a stupid question, it's just, one's not even worded to where you can make sense of it.
Well, that's what we are going to dive into. Okay, so let's just go back, take a quick look at the week 1 homework, bringing everyone up to speed. This one's fairly straightforward, so we're looking at the specific volume versus the density. So the specific volume, as we mentioned previously, is just the inverse of the density, and we're just comparing 2 gases. One thing to note is that hydrogen is the least dense element on planet Earth.
Something I have in common with
Okay, so let's just look at the solutions.
What, week 3?
Well, I'm just starting from the top here, so I'm just looking at that very first week 1 homework solution. So there's the density of hydrogen, and again, the density is just 1 over the specific volume. So we just take the specific volume, which was given, take the inverse, and there's the density in kilograms per cubic meter. Same thing with methane. The density is given in pounds per cubic foot. We convert by looking at kilograms per pound, and then cubic feet per cubic meter. And there you go. That's the density of methane. And the way this is read, or the way that it's written, was kind of strange. I'm not sure why Brian.
Well, you must have 3 different answer keys there because we must have different questions, because I only got the first one.
You only got the first one?
Only got the first question, yeah. It's the density of hydrogen.
Well, let me wrap up the full solution, then we can go back and address that question. But the question was how many more times dense is methane than hydrogen? So you just look at the ratio. You could either, and there's a couple different ways to do that. You could look, in the way he's written the solution out, you subtract the smaller density from the larger one and divide by the smaller one to look at the percent increase. I'll also give you credit if you just want to look and see how many more times methane is than hydrogen. So just dividing 0.071 by 0.0909 is also a valid answer. Just comparing the densities. And you're saying you only saw this portion? Huh. I mean, I'm not sure why. I mean, did you have? I mean, when you and I reviewed this, all this has been there.
I added some help, but I did the third one. And you subtract both the densities and then divide by the denominator, the bigger density, because methane is, the hydrogen is in methane. What is the chemical formula for methane? Like,
Oh, sure. Yeah, and
CH4?
I think one,
Hydrogen is just a component of the methane.
yeah, and one thing to make clear here is that hydrogen in its gas phase just looks like this. You know, the hydrogen, it's always H2. So you've got two hydrogens sitting by side, going back to the dynamic periodic table. If we just go and look at the orbitals, that's usually the easiest way. Go and look at hydrogen. It just has a single up electron in its 1s orbital, so it will combine to more or less form helium. So sometimes helium is sitting all the way over here on the with the noble gases. This one's just for whatever reason it's sitting here. But the more stable elements will always have a full outer shell. So there you go with the 1s orbital full. Same thing happens, we'll pop out to neon. You can see that the 1s, 2s, and 2p are all full. Same thing right on down the line. So just looking at hydrogen there and saying, oh, it's got an empty orbital on its 1s leads you to the conclusion that hydrogen is more stable in a diatomic form as a gas. So then moving on to methane. Methane is CH4. So this is what the, so single carbon sitting there with 4 hydrogens around it. If we take a look at carbon's electron structure, you can see that its 1s and 2s shells are both full. The 2p is missing 4 electrons. Well, where do they come from? They come from the 4 hydrogens. And so now hydrogen feels or acts or behaves or whatever more like helium, because it's basically grabbing or sharing one of those electrons in carbon's 2p orbital. And carbon gets to feel a little bit more like neon, because now it's got those 4 extra electrons from those 4 hydrogens hanging around. Okay, so that, and I don't know all of the details on what.
So could you burn neon too?
Could you burn neon? No, neon is inflammable. In fact, I think if you could probably have a nice fire extinguisher with neon if you had a neon spray it as a good fire suppressant. At least that's I don't know. I've never tried it, but that's from my knowledge of. And it's the same thing. If you had argon, it's inflammable, and it would act as a fire suppressant. Okay, so in terms of why hydrogen is less dense than methane, I don't know. I don't know all of the molecular mechanics behind that, but it just means for a given volume of space. One way to think about it, actually it might be here. Yeah, if you go out, it might have something to do with the radius, although all of these radii, I believe, have just to do with the elements themselves. You could go out and look up the sort of average volume of a single hydrogen, H2 molecule, add those up, and then from that volume you could then extrapolate how many kilograms there are per cubic meters. Each hydrogen atom itself has an atomic weight of 1, so from there you could go out. But one way to think about it, the density, it just could be the way these guys are packed together. And don't get the impression this is some kind of solid. All of these molecules are moving around. In air, the average velocity of air molecule is something on the order of, what is it? It's actually greater than the speed of sound. It's on the order of 1,200 or so feet per second. the average velocity of air molecules. So the same thing is happening in a gas. It's got, moving around, bouncing around. And when it comes down to it, the density is greater. So you could almost think the reason the density is greater for methane versus hydrogen, all of those protons are just kind of hiding in the nucleus, where you've got 6 protons hanging out in the carbon nucleus. And 6 neutrons. You've got, sort of an AMU of 12 down here. 12. You've got an AMU of only 2, and right there is a 6-to-1 factor. And if we go back to the solution, that's sort of one kind of easy way to get from that nanoscale of what the protons look like down in the methane and hydrogen nuclei versus what we just saw with the solution. So let's just take one more look at the solution. And there it is, 6 times, 6, almost 7 times greater, or actually a little more than 7 times greater density. So that's one way to, get from that nanoscale with protons sitting in the nuclei all the way up to the macro scale, these gases that we can use for renewable energy. And both of these will burn, by the way. Both hydrogen and methane will burn. And the difference, it's very simple. If you just take H2 plus O2, those burn, you end up with H2O. So how do we balance that? Well, we've only got we've got 2 oxygens over here, and let's just go back and look one more time at the dynamic periodic table and decide why oxygen sort of behaves the way it does. These 2 outer electrons with oxygen more or less just bind with the other 2 outer orbitals. So if we draw the structure of oxygen, let's just go ahead and do that. So here's your oxygen, and you've got your 1s and your 2s are both full. So there's your 1s, and it's got a up electron and a down electron. Here's your 2s, it's full with an up electron and a down electron. Now the p orbitals, let's see the best way to draw this. Probably the best way to draw it is just to have this orbital full with an up and a down, and we can call that the vertical, if you will. And then these guys, let's draw it this way. Let's just draw the sort of the front to back orbital like so, and let's just say there's 1 electron here, but a missing electron over there. And then let's just draw that 3rd p orbital. Start here, come through, come this way, and we'll say there's an electron here, but a missing electron there. So let's see if I can just grab that whole thing.
Is there another class period for this class this week?
Yeah, alternative fuels meets twice a week, Tuesdays and Thursdays.
So this Thursday, would we be going over this week's homework?
Yeah, we will. We sure will. Yeah, I'm just catching up on getting us up to speed on the rest of the class because we haven't had a chance to cover the solutions yet.
Okay.
Yeah.
All right, well, I'll be here Thursday.
Okay, sounds good. See you, Serenity. And so if we just, and what I'm trying to do, I'm trying to get
Wow, I
my,
didn't recognize him.
trying to get my copy tool. Yeah, you got a haircut. Okay, let me see here. Give me one quick sec. Okay, I found the selection tool, and what I'm trying to show here is that second oxygen atom. So I showed the 1s and the 2s are down here, and they're all full. They're all full, and they're not really what's affecting the chemistry of this oxygen. The 2p orbital has 1, 2, 3, 4 electrons in it. And we see that if we go back, we can see right here in the 2p, there's 1, 2, 3, 4. So same thing, 1, 2, 3, 4. And now essentially what happens, these missing electrons for oxygen end up more or less sharing. So you could, and it's, the electron cloud obviously looks different. These orbitals combine in such a way that, let's just say part of the time, this 3 electron could find itself occupying this state over here, and this 2 electron could find itself occupying this state over here to form a larger diatomic oxygen. And it'd be great and fun to go and look up what the structure is, but it's kind of beyond that. Ozone is O3. Ozone, you've got a third, third one in there. Okay, but to balance this equation, we can see that we've got 2 hydrogens on the left, 2 on the right, that's fine, but we've got 2 oxygens on the left and only a single oxygen on the right, so what we need to do is double that. Therefore, we have to double that. Now we've got 4 hydrogens on the left, 4 on the right, 2 oxygens on both sides. So for every oxygen atom that is burned, you need a pair of hydrogens. And there's that. So those guys become
2-to-1 stoichiometry.
stoichiometry. There you go. Okay, so that's the combustion for hydrogen, and then the same thing. Let's go with methane. So here's C, H, 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 and we'll just start off with a single oxygen. There's that double bond that I was showing, where you have these electrons being shared between the 2 atoms. Now we know that the 2 combustion products are CO2. So here's this guy, here's that guy, there's your famous CO2 molecule, and then we know H2O. So there's your water molecule. And then to balance that, the carbon looks good, there's just a single carbon on each side. There are actually 3 oxygens hanging out, so we're going to have to increase that somehow. We've got 4 hydrogens. So what if we go ahead and double this? So I'm going to stick another water out there. Now I have 4 oxygens on the right. I have 4 hydrogens on the right as well. So the hydrogens are balanced, the carbons are balanced. The only thing I need to do is bring in another oxygen atom, and then I'm all set. So that's more or less what the stoichiometry of methane combustion looks like. So I had to have 2 oxygens for every methane, whereas it's just kind of the reverse, where I need 2 hydrogens for every oxygen to get complete combustion for hydrogen. Okay, so that is, that's week 1. That's the week 1 homework. And then we've already covered the week 1 quiz. That's fairly straightforward. So I'm going to go ahead and stop the recording, and then we'll cover week 2.